Good evening, everyone. As the director of Goethe-Institut Max Müller-Bauwahn, Mumbai, I'm having the great pleasure of welcoming everybody present here, as well as our virtual audiences, to the third literary intervention in the framework of State of Nature. State of Nature, which, as the name suggests, is based on ecology and climate change, and ventures in its current third iteration since 2018 into multidisciplinary culture production and its associated conversations. I would also like to mention that the related exhibition, titled New Natures, A Terrible Beauty is Born, is on view in our gallery and the Natural History section and lawns of the CSMBS till mid-April. It includes the works of 17 young and senior contemporary artists dealing with ecology from different perspectives. The exhibition is curated by Ravi Agarwal and the literary interventions by our curator of literature, Ranjit Hoskote. Today's lecture is by Pranay Lal. He is a biochemist by training and works for a non-profit organization on public health. He has been a caricaturist for newspapers, an animator for an advertising agency, and an environmental campaigner. His first book, Indica, A Deep Natural History of the Indian Subcontinent, was published in December 2016 and won multiple awards. His most recent book, Invisible Empire, The Natural History of Viruses, was released in November 2021. Dear Pranay, I'm happy to have you virtually with us tonight, and now I wish all of you an inspiring and enjoyable evening. Thank you very much.
Thank you to the Bhavan and to the Institute for inviting me. And of course, thank you to Ravi and Ranjit for being kind enough to believe in me that I may have something to present and to talk about in terms of deep natural history and the repercussions it holds in terms of what's going to happen in the future. But I'm going to take you into deep past. If you really want to understand what's going to happen in the future, let's try understanding what happened in the past. I'm going to start sharing my screen. So I'm going to give you a deep natural history perspective of how we came to be and why life exists the way it does. And of course, this is entire 4-hour lecture by itself, but I'm going to be very quick in terms of what has happened over the 4.5 billion years since the Earth has come into existence. So I'm just going to be showing you what happened, when the Earth had just been created and it was revolving in its orbit. The orbits were not firm and there were no definitive paths, and many planets and planetary bodies had errant pathways. And about 4.56 billion years ago, a planet called Theia came and collided with a very early Earth called Proto-Earth, and it caused the biggest explosion in the history of the solar system since the creation of the solar system itself. And what this did was that it caused the two planetary bodies to melt away, and it took about 100,000 years for both of them to reform, to anneal together and form two bodies again, about the same relative size. And one became the moon, and the other was our planet Earth. But this was a moment which was absolutely decisive and critical for why Earth became the way it did. The Earth inherited several features from this explosion. The first was that it developed a core in the heart, in the center of the spherical Earth, which is alive and it's wobbling and squishing around with molten lava. It's called, this core is made up of iron and nickel and silicates and, chemicals which are molten and extremely, extremely hot. And gradually this heat started to dissipate and it developed layers. So there was a segregation and there were layers that were created. And the core by itself continued to slosh around. And this made Earth very, very much alive. The moon, a relatively smaller body, lost its heat very quickly and it dissipated its atmosphere. In fact, Earth stole moon's early atmosphere and we got there helium and hydrogen. But the other features that the Earth developed was a tilt, which is 23.5 degrees that most of us would remember from our geography lesson. And it ensured that the Earth stayed on a relatively stable path. And gradually, the Earth at this time started to cool down, and it took about 500 million years. I mean, 500 million years is from 4.5 billion years to about 4 billion years. The Earth started to cool down slowly. But even then, the temperature was still high, and Earth was still being pummeled by meteors and asteroids and other planetary bodies. And what this did was it introduced new elements from outer space, what are called rare earths, things like gold and diamonds. But the most important thing, the most important endowment that happened at this time was that the Earth started to acquire water. Volcanic activity and meteors gave Earth its whole quota of water that we have today. The other event that was happening, this is about 1 billion years later, this is about 3.5 billion years ago. There were volcanoes all around the Earth, under the water in the shallow oceans that were forming, as well as on the surface. And there was a lot of noxious gas that was coming out of these volcanoes and from the vents in the below the sea. And these started to add new complex elements to the atmosphere. So the atmosphere began to form. And remember that this time is still very, very hot. We're looking at temperatures about 100 to 70 degrees centigrade. This is a time when Earth was absolutely inhospitable. But gradually, and very, very gradually, there were some signs of life that was beginning to emerge 3.5 billion years ago in some parts of the Earth. And life would have sputtered and died out and started again. So it was a process that was not a directed one, but it was an accidental process, perhaps happening in deep ocean or seas or in the edge of where water met land. But the point that I'm making here is that the arrival of the first cells enabled to create an environment where the cells would eat into minerals and create new minerals, what was called biomediated evolution. We saw a fascinating amount of new rocks and new kinds of rocks to form. And among these rocks were rocks like these, the ones that we see in the Aravallis. Now, this is a classical rock in which you see that the rock has been heated and reheated. And you see in the center a dark patch, which is a heavy metal, a metal ore in the center, and the lighter metal ores that have dissipated towards the outer side, which have been, it's like a bit like a filter paper. The other thing that happened about 3.5 billion years ago was that the cells that were forming started to form partnerships. And some of these were better at utilizing noxious gases like methane or ammonia or hydrogen sulfide, and would produce oxygen as a byproduct. Oxygen was a toxic gas for these chemical breathing single-celled creatures. As an evolutionary step, there were some creatures, some single-celled organisms that evolved eating into or breathing the oxygen that was being taken out by these chemical breathing bacteria. So you had the first oxygen breathing, oxygen utilizing bacteria that emerged. And one of the things that they did very quickly, an innovation that is absolutely crucial if we are going to talk about climate change in the future, is photosynthesis. So one of the critical things that developed was photosynthesis using carbon dioxide and water to release oxygen and make sugars. Now, these creatures therefore became the primary producers, and they remain the critical building block for not only the food that we consume, but also for consumption of carbon dioxide and production of oxygen. Now, these creatures lived in colonies. They would look like cabbages because, this is a fossil from a place called Sonbhadra in Uttar Pradesh. And the yellow chemical that you see, the mineral that you see is phosphate. But these would be massive colonies, and they would produce so much oxygen that they caused more water to be produced. They caused the first atmosphere, which was oxygen laden, to become stable. And they created the ozone layer. What was very important was that they caused the Earth to intermittently freeze many times over. And from the period 3.5 billion years till about 750 million years, Earth was relatively cool. And it was only around 750 million years ago that a massive volcanic event caused the Earth to be liberated from this icy freeze, and microbes became more evolved in a sense that there was a massive genetic leap that happened, and multicellular life emerged. So the dominance of these single-celled creatures from 3.5 billion to 750 million years, that's about 80% of the Earth's existence, was dominated. The life that was dominated was by these single-celled creatures and their partnerships with other single-celled creatures. And they formed these colonies, which were magnificent. There's some reminiscent of these in Australia and the Bahamas and a few other places. Otherwise, these colonies of microbes has now gone extinct. But let's come to the phase that we now are quite familiar with. This is a site that we all see in most developing countries. And this is the phase from the time when human beings domesticated fire and evolved methods in which they could make bricks and porcelain and other ores and minerals that could be smelted. And they started to make more complex compounds. From the period of 1750, the time of industrialization, we've been adding more and more chemicals to the environment. So many chemicals get added that there is now no record, no official record of how many chemicals actually are there in nature. There's one estimate that there are 12,000 chemicals that are added every year to the environment. There are new chemicals that are added and for which there is no known environmental fate. The estimated chemicals that in terms of the entire numbers that exist today, completely synthetic, are about 12 million chemicals. Now, these include plastics and fertilizers and pesticides and antibiotics and dioxins, and the list goes on. Now, I just want to summarize what I just said. So you recall the image where the Earth collided with errant planetary body, and that at that time we had about 350 minerals or so. But once the volcanic activity was working, and that was reworking the rocks over and over again, we had another 1,200, 1,500 minerals. But when oxygen and life emerged and oxygen got added to the atmosphere, we had about 4,500 minerals. Now, it's in this age that we have added more chemicals, and this accumulation of synthetic chemicals is the one that endangers the entire process of what we now know as biogeochemical processes, where biology and the chemistry between the different types of ores and the action of the microbes and any living matter is now being compromised because of synthetic chemicals that is accumulating in such large numbers. Now, the challenge before us, therefore, is not just the fact that we are compromising the processes of nature by diverting rivers or extracting biodiversity or decimating wildlife or forests, but a more persistent problem where recovery is possibly going to take a much longer time, or perhaps there may be no recovery because we are leaving behind chemicals which Life forms by themselves do not know how to digest, accumulate, assimilate, and break down. So the challenge before us is the amount of chemicals, whether they cause global climate change or not, that's another matter. But the fact of the matter is that we are now looking at chemicals which have no environmental fate. I'm going to put before you three propositions today. And these propositions are about how we view biomes and how we look at different cultures and how we look at different pressures that we pose on the earth. Now, if we were to look at the earth over the last 200 years, now the darker you see in color, the maroon on the terrestrial ecosystems, on land, if you were to look at this, the places that are the most brown maroon in color are the ones that are most worked and reworked and degraded over time by human action. And the same thing, if you were to look at the darker blues that you see in oceans, means that the ocean has been abused and over again by human action. So very few parts of the world actually are in the light yellows on land, and very green, the dark green is absolutely nearly absent, except for a few specks that you see near Antarctica or right on top in the Arctic. And there's very, very few specks that you see perhaps in Australia and in Baffin Island and Newfoundland and places like those, that you have a very light yellow speck which says that this is relatively untouched by humans. So this is the level of influence that a single species has been able to do. So perhaps after the single-celled photosynthetic bacteria, about whose introduction I've just given you, which caused the creation of the minerals, the oxides and the carbonates, human beings are the other major force. And we are not sure in which direction the force is being applied, whether it's going to be positive for all living creatures and for human beings themselves or not. Currently, the opinion is that we are not going in the direction where evolution and nature's processes are going to be conserved and for posterity. So like I said, I'm going to make three propositions to you. The first one is going to be about rivers. And what we know about rivers is, of course, that they're there for us to provide us with clean drinking water and navigation and hydroelectric power. And we can change the course of rivers as and when we like, or extract as much water as we want. But before we get into looking at the cost benefit of rivers and the various cultural aspects that are attached to it, I just want to take you back about 250 million years or 300 million years ago. And this is how typically a forest would have looked like in the age which is called the Permian. Now, this is the period when the southern continents, what's called the Gondwana land, which comprised South America, Africa, India, Australia, Madagascar, and a few other smaller land masses. Now, this is what typically the forests would have looked like. Now, the forests at this time were non-flowering plants, largely like cycads and palms and lycopods and mosses and ferns, those kind of plants that you see in gardens even today, but they were giants of the time. At this period of time in history, these plants lived very close to lakes and rivers and seas, and there was a constant flooding that was happening. When a constant flooding would flush down a swathe of vegetation, a swathe of forests, and deposit this huge amount of vegetation into depressions. And with subsequent deposition taking place every few 100 years, the decomposition because of heat and pressure and the microbial action created an environment of very strong decay. And this, over millions of years, transformed into coal, into petrol, into natural gas, and many other forms like lignite. Now, why am I telling you this? The reason why I'm telling you this is that the history of carbon, our problem just now, which is center to global warming and climate change, is the way we utilize carbon. And the single source of energy just now, the single largest source of energy just now, still remains carbon. And utilizing something from the deep past, something that was made 250 million years ago or earlier, was extracted from the depths of the earth. Now, when we bring it out from deep, from say Bombay High, I mean, I'm sure some of you would have seen the Bombay High, or if people who've joined from Kochi, you know, the Kochi High is there. And of course, if there's anybody from Assam, you know, the Digboy crisis that happened 2 years ago. So the point that I'm making here is that we take out carbon from the depths of the earth, but we never put it back. What is called carbon burial. This is the fundamental flaw that we have in terms of fighting climate change. We take the carbon out, we emit it in the atmosphere, and we want to capture it and keep it back on the surface by planting trees or conserving tropical forests, and even using technological measures like direct-to-air capture, which is now increasing in prominence. But the challenge remains that anything that we keep on the surface means that it can be dissipated very easily back into the atmosphere. So our challenge is that how is it that we put back the carbon that we have extracted from the depth? Now, with this background, I want to take you to a journey of how one river in particular has done incredibly in terms of burying carbon silently and quietly, and yet we don't recognize its services. So I'm going to take you, into the 1950s. Now, this is, I'm sorry, I'm, showing you this chemical reaction, which is actually very boring to look at. But if there is a chemical reaction that we should be teaching children or learning it ourselves after perhaps photosynthesis and respiration, it's this one. Now, it's a very simple reaction. Please do not let it, mess or muddle with your mind. It basically says that if a compound like a silicate, the one that you see on top left, which is calcium silicate, combines with something called carbon dioxide in presence of water. Now, water descends on Earth in the form of precipitation like rain. Now, when rain falls on the Earth, it combines with carbon dioxide and it becomes a dilute acid called carbonic acid, right? Now, when it falls on the Earth, there are places on rocks and sands where it will combine and cause to form something called calcium carbonate, what we know as chalk, marble, or dolomite. It's known in several forms, and produces another thing that we see very often on the beaches, which is silicon oxide. Now, Harold Urey was a remarkable chemist. He was a chemist in the 1930s to 1960s, and he was a polymath. He won the Nobel Prize for purification of the uranium and other radioactive chemicals at the time, just before the World War. But his interests were largely in planetary systems and understanding astronomy and the way in which nature worked. And while giving a lecture in Columbia University, he asked an art historian, a very prominent art historian, of how does he explain the use of so much or existence of so much marble in the world. And the historian said, listen, I don't know this, but perhaps a geologist would know this. Urey did not find the answer to this, but then he started to think from his chemical training, from his training in chemistry and other disciplines and sciences. He thought that there would be some action in which water and carbon dioxide would be acting. And so he came up with this very elegant equation, which explains where and how this process takes place. The challenge for Urey at the time was that he did not know that what was keeping carbon dioxide in balance at the time. He knew that photosynthesis was there, but the industrial processes especially was something that was adding an immense amount of carbon dioxide, and there has to be something that subsumes the carbon dioxide other than plants. And when he proposed this equation, he knew that there were landscapes that could do it, but he could not pinpoint where on Earth's land surfaces could this be. And the answer comes from our river that we all know very well. It's the Ganga. Now, the Himalayan rivers are young. The Himalayas themselves are very young. I mean, you know the story that, you know, the Himalayas rose because India collided with Tibet, and over the 40 million years when the Himalayas rose and became the tallest mountains, the granite that got created was young, it was friable, and the action of the carbon dioxide and water, what is called a weak acid called carbonic acid. It's like the colas that we drink. It's slightly less acidic than that, but has the same etching effect. Once it falls on granite, it causes it to strip out silica from it. And the carbon and the silica combine and stay in a dance till, and it requires a lot of energy, which is not available in aqueous environments to break it. Now, once this solution or these minerals reach the mouth of the Ganga, they are flushed down because of heavy monsoon rains that happen, or monsoonal floods that happen. We've got violent rivers like Kali and Arun and Gandaki and others that flush down a huge amount of volume. And of course, the Brahmaputra also winding down from the eastern margin. It also carries a minor load of silica. But the single largest burial of carbon that happens is because of Ganga. That's because just two rivers, Arun and Bhagirathi, have young granitic rock, which combines with this carbon dioxide that the water, the rain captures as it falls down. Now, it's not just that it captures the water, but it also goes deep into the ocean, the Bay of Bengal. The power of the Ganga and Brahmaputra in the last 30 million years has created massive submarine gorges, most of which have not been mapped as yet. And they're deeper and wider and longer than the Grand Canyons and any other canyon in the world. There are very few canyons. There are some canyons in other planets which can rival it. But the canyons that are underwater, off the mouth of the Ganga Brahmaputra delta, are deep. And this is where the complex compound of calcium, silica, and carbon dioxide goes and embeds itself in the depths of the ocean, and it rises only when it is perturbed. And it's not been perturbed for about 30 million years. Now, the reason why I bring this up is if you were to look at this image, notice on both sides of India, you see these large sediment fans. Now, together, the Indus and the Ganga used to bury the most sediment in the world. Even today, they do. Indus, unfortunately, has become a weak and has lost its power. Indus used to be a more powerful river till about 5 million or 4 million years ago. It's only recently in geological times has Ganga picked up and increased the deposition and the chemical reactions that happen along its banks. But look at the power with which it flushes down the sediments. And this is one reason why we find an amazing variety of invertebrates, because invertebrates, especially shelly creatures, require silica to make their shells and bristles and thorns and spikes and spikelets and all those things that go into making these very tiny creatures that are shelly or have a shelly coat. Now, this is one reason why people who study mollusks and invertebrates were not able to figure out that why is it that we find such an amazing variety of invertebrates, marine invertebrates, in Indonesia and the Andamans and along the Bay of Bengal. And this is one reason that perhaps we can now attribute it to. Now, I'm going to rest this story, but I want you to remember these facts because I'm going to call these out again because my three stories are interlinked. So my second story is deserts. Now, the word desert is both a noun and a verb, and we treat it just like that. It's a forsaken place, and we do not have any respect for deserts the way they are. They are a dust bowl. They need to be greened, and we should protect our cities from the onslaught of advancing dunes. All of that is correct. We have to protect our cities, but going overboard by planting trees and grasses is something that I want to present as a case that deserts do more than that. So my first point that I want to take you is back to 55 million years ago, the time when before India was about to collide with Asia, or Tibet rather. Now notice from the place where today we have Shanghai till about the place where there is Gibraltar or Spain, there is a sea called the Tethys. It's a thin ribbon-shaped sea that extends from nearly halfway across the earth. Now, this was a very important place because a lot of mammals evolved along the banks of the islands and the landscapes that exist here. The whales, for example, evolved in the region in this area, the elephants, the rhinoceros, and even the primates. Now, that's not the story that I want to tell. The story that I want to tell you here is that because the land masses were separated at this time, you've got South America still not linked with North America. Africa and Arabia are joined together, but they are separated from the Middle East. The Middle East is still to rise. India is still a distance away from colliding into Tibet. Now, you would imagine that the ocean currents that would have existed at this time would have been smaller and not as intense because the seas are shallower. But as the land masses move, let's look at more contemporary times, you notice that the Earth has, the first time when the current land masses come into place, the Earth has deep oceanic currents. And what happens then is that you have another major ice age, which is called the last glacial maximum, 21,000 years ago. And this is the time when Arctic gets its ice, Antarctica becomes a permanent ice cap, and it's a massive, massive icy region. Now, the closing of the Tethys caused the deserts to form. Now, notice on the left, the desert in the heart of Africa is a very tiny one, right? Now, this image is for about 40 million years ago, or 50 million years ago, when Africa and Saudi Arabia have not collided into Asia Minor. But when they collide and close the Tethys, the circulatory patterns of winds and oceans desiccate these massive continents. And as a result, there is less moisture that's moving into the center of these large continents and subcontinents, causing the deserts to desiccate and expand. Now, having this event is backed by also the ocean currents that are formed and rather manipulated by the massive ice shelves in Antarctica. What happens is, notice that in the southern hemisphere, cold currents that move anti-clockwise desiccate any continent that they pass through. For example, look at South Africa or South America, and you see the Kalahari and the Atacama. But in the north, it's the other way around. The cold current, as it passes in a clockwise fashion, desiccates the continental margin. So you see Africa, again, you've got the Canary Island current, and you've got the California current, which creates the Chihuahua and the Sonoran and the Nevadan deserts. And likewise, I mean, the same is true for for Australia. Now, Australia did not have a desert until 20,000 years ago. Thar and Sahara and much of Horn of Africa and Arabia did not have deserts. The only permanent desert that was there was the Gobi Desert and a small strip in the Andes because of the rain shadow effect rather than, and this was because of isolation and the distance from the sea and monsoonal rains not being able to reach there. It's not because of the desiccating effect of the ocean currents. There's another thing that happens because of air circulation. Now, these are called Hadley currents that move from the equator and they carry the moisture from the tropics to the center of the equator. Now, I'm going to stop here because this is getting very theoretical. And I know you're getting bored, but I just want to come and show you this. Now, imagine this happening every year for 4 to 6 months. This is dust traveling from the Sahara towards the Caribbean Sea and into the Amazon desert. It goes as far as the Galapagos. In fact, when Darwin traveled and crossed Tenerife Island, he said that he was not able to see the horizon because of the dust storm. And when he reached the Galapagos, he found similar sand to the one that he found on the deck of the Beagle. And since then, several people, including old ship records, have spoken about beach sand that has been transported onto the ship. And there's several records of that. Now, what I'm trying to show you here is the power of the deserts. Desert sand travels for millions of miles, and about 500 billion tons of desert dust is transported every year, of which 95% is from the Sahara and the Saudi Arabian desert. Now look at this, something closer home for those of you who are in Bombay. This is the desert sand leaving the Horn of Africa and Saudi Arabia and coming to between Karachi, Gujarat, and Bombay. And just before the monsoons, there is a huge surge of sand from these deserts to the Western Ghats. Now, what the sand does is it fertilizes the oceans and it also nourishes the evergreen forests. Now, wherever this sand lands, this enriches the soils. The tropical soils are actually drained of nutrients because there is so much water that is entering them and leaving them on a very regular basis with immense power. It's only nourishment of new elements, especially silicates, iron, and phosphate that's coming from the desert sand that nourishes the trees and the plants and the life in tropical forests. So tropical forests owe their existence to deserts. If we were to stop this process, if we were to green the entire Sahara, we would also be compromising the deciduous and the tropical and the wet evergreen forests of Africa, South America, India, Indonesia. So this is a very important fact that I would like you to remember. And please remember that I'll come back to this aspect in my closing point. I'm going to come to my next proposition, which is I want you to look at oceans. Now, before we begin looking at oceans, I want you to look at this statue. This is from Bandhavgarh. This is the statue of Vishnu, the preserver and protector of the universe. Now, as he reclines and overlooks this pool, which looks stagnant and boring, and it's actually covered with slime, it's this slime that is the most crucial thing for us. The reason why I say this is you would recall that when I was talking about the biomediated creation of minerals, when all the oxides and carbonates were created, when the microbes, the photosynthesizers produce so much oxygen. It's these small, humble, green creatures on the top of lakes and oceans and ponds and seas that produce all the free oxygen that you and I breathe. This is important because there are creatures that we don't even know about. Now, for example, the creature on the left, it's called Prochlorococcus. Pro means first, chloro is green, and coccus is rounded cell. Now, Prochlorococcus and Synechococcus are related blue-green bacteria. Together, they produce about 24% of all the free oxygen that exists on Earth. And there are several other like them. There are about thousands and thousands that we are just still discovering the new cyanobacteria that exist in oceans and seas. Prochlorococcus and Synechococcus float around in the top 8 meters of the oceans and seas. Next to it is another, that fuzzy looking thing is Trichodesmium. It's a thin, long creature, microscopic, which is very, very difficult to see unless it's cultured in a lab. And this is the single largest driver of the nitrogen cycle in the oceans. And to the right is Microcystis, another small, actually a very beautiful creature. If you were to see it under a microscope, it looks like a chandelier. The colonies of Microcystis look absolutely beautiful. What this does is it synthesizes and regulates the sulfur cycle of the entire planet. Now, I want to show you this image again. You remember the colonies that we were talking about, that the blue-green bacteria formed with other chemical synthesizers, the chemical microbes. Now, this produced all the oxygen, right? And this is the story that is continuing even now. Although stromatolite by themselves have become near extinct, there are very few remnants, like I mentioned, in Australia, in Bahamas, and a few other places. They seem to not exist anymore because there is predation by other creatures, especially mollusks, which now devour stromatolites. It's they make for a very easy prey. But the point that I'm coming to is that it's the blue-green bacteria that surround the oceans and the rivers and lakes and seas and just about everything, the ponds, that produce all the oxygen and subsume all the carbon dioxide that is produced in the world, whether it's from natural or unnatural sources. Now, this is how they're distributed. They are affected by heat and by ocean currents, but of course, by things like shipping channels and pollution and radioactivity and dumping of plastics and things like that. Now, we are challenging the dominance of a humble creature, which until the 1990s was not even known to exist. Prochlorococcus was discovered in only 1998 by a PhD student at MIT, and its cousin Synechococcus even later. So we don't know enough about the oceans and its inhabitants, but they continue to do the work that they do. But for every creature that lives in the oceans, there is something that feeds on it. And the massive consumers of this is something called the lanternfish. These are bioluminescent fish that live in deep oceans, and they wait for darkness to occur, and they come to the surface only at night to feast on this blue-green bacteria that have fed on the sunlight and become bigger, and they start to multiply. And that's the time when the lanternfish come up and start feeding on them. Lanternfish then descend as the sun rises to go down and catch on any blue-green bacteria that are descending either through death or because of their weight. And they start to feed in the zone which is called the Twilight Zone, where there is very, very little light. And their their display of their bioluminescence is not only for communicating, but it's a very efficient indirect way of also expending energy, because they also signal where is more food, or where there's a large swathe of blue-green bacteria to their colony members. But there's another creature that eats in copious quantities, and these are baleen whales. Now, baleen whales, as you know, eat plankton and diatom and cyanobacteria. They are filter feeders, right? So although these are macro. They are large multicellular creature, and a single gulp of a baleen whale could be a few thousand liters. There's nothing that compares to what actually is the single largest predator in the world. That predator is a virus. Now, every given second, there are 10 to the power 23. That's an unimaginable number. 10 to the power 23 infections that are happening of Prochlorococcus and Synechococcus on Earth. Now, what that means is that the viruses that you see, these satellite or rather space lander shaped viruses that you see at the bottom, infect these cells. But what they also do, they don't just kill randomly. They kill cells that have grown during the day and are either in the process of multiplying into many more cyanobacteria or blue-green bacteria, but also as they attack a bacterial cell, they also instigate it to produce one last time. So instead of just one cell dying, it ensures that a couple of other cells have been created, or rather been manipulated to create more. So this super fecundity in the oceans is actually orchestrated by viruses. So the overlord, the dark overlord of the ocean, causing the death of billions of cells. Actually, there's not even a term for 10 to the power 23 per second. It's an unimaginable rate of infection that's happening every second in the oceans, right? So what happens when the bacteria get killed is that they sink to the bottom of the ocean. And this is where the deposition, the deep carbon burial of something that has captured carbon during the day happens. Now, we need to see this in a bit of a perspective, because what is crucial is that we need to take a stock of where the carbon is, right? Now, what we know in terms of carbon is that the carbon resides in the atmosphere. And we know that roughly 750 gigatons, and a gigaton is about 1 billion metric tons. So 750 gigatons resides in the atmosphere. That's how much carbon dioxide is in our atmosphere. But the oceans hold 40,000 gigatons. The biosphere, that means the trees and grasses and other living things, about 610 gigatons. And the soil, which is also a remarkable ecosystem, about 1,600 gigatons. So 97% of all the carbon that is there on the surface of the planet is in rivers, seas, ponds, oceans, and water bodies. So the green slimy thing that you see on top that's producing oxygen for us and sinking our carbon actually is doing us service. And the oceans and the open seas, which we think are actually wastelands that need to be reclaimed and can be used as a dumping ground, is actually a pretty bad idea. I'm now going to move to my final proposition. And I want you to take a look at this image as well, because not only does the dust, so if you were to look at this image, the image shows broad arrows that are, for example, on West Africa, you see the biggest arrow. Now that's the dust that is coming from Africa, the sand grains that are flying because of the massive dust storms that happen across oceans. What these dust storms do is they actually fertilize the ocean, but they also fertilize the forest, like I mentioned earlier. And this is critical for the nitrogen, phosphorus, sulfur fixation in the oceans, which indirectly also cause the burial of carbon. And the burial of carbon that happens here is near permanent because there is very little turbulence that is happening at the bottom of the ocean. Unlike the surface of the land, where you have trees which can be cut and be made into furniture or be made into paper, or forest fires decimate large swathes of land, which therefore releases carbon dioxide. So carbon that is being fixed in oceans is more permanent and more stable than the carbon that we are trying to fix on land. So this fixation with land and fixing carbon on land alone is a misguided one. I'm going to now try summarizing what I've said, and I apologize for any pontification if you think it is that. But I think we've got a science a little wrong, although we know for a fact that several discoveries have been made, especially like the one about the Antarctic current, the role of the Ganga, for example, in capturing carbon dioxide, or the role of the deserts. Now, all of these are kept outside of the purview of policy making. And it's the most populist results and solutions that are adopted. You'd be surprised that the whole silicate cycle, the one that I showed you about Urey's reaction, did not find a mention in the IPCC, in the climate change discussions, till about 2018. And we've been a little too focused on capturing it and capping carbon, both at source or by capturing it on terrestrial bodies, like planting trees or grasslands or conserving tropical forests. But the role has to be now a little more focused, and we have to look at how do we want to pack back that carbon that we've released by burning fossil fuels back into the depths of the earth. So I think our science needs a strong rejig before we can actually say that we have a clear roadmap of how we want to deal with climate change. I'm not a big votary of net zero and circular economy or sustainable development, because this is something that is more like accounting rather than real service to nature and its processes. Like I mentioned, I think we need to look at global commons, which provide services which are amazing and which we take for granted. And we need to ensure that they stay stable. We therefore need comprehensive strategies on how we want to leverage geological and ecological processes to combat climate change. And finally, I think there is a massive conflict of interest, especially when corporations and corporation-backed think tanks and civil society decide on the roadmap of how net zero or climate change has to be achieved, or reduction or mitigation of climate change or capping on carbon has to be achieved. And for this, because markets depend on economics, we need a more robust and a more transparent framework on how we decide on the price of carbon. And we should actually prevent transfer pricing of carbon. That's a notion that has actually been disastrous for even the stock markets. And I think we now need to start valuing nature services a little more differently, and not look at biomes and landscapes of what we think are of value. Rather, we should take a longer view from the deep natural history perspective to understand how different ecosystems are linked. Who would have thought that deserts actually contribute to how tropical forests like the Amazon or the Indonesian forest would flourish? Thank you so much for this opportunity, and I look forward to any questions you may have.
For one, Pranay, I just want to thank you for both the technical depth of your presentation, but also the manner in which you communicated it very elegantly and forcefully, and also for underlying themes that have come up again and again also in the course of the conference that we had as part of State of Nature. Amit Pangshu, Acharya, and Rahul Ranjan, for instance, dwelt on rivers. We also spoke of, for instance, our own Forest Act here, which is completely non-cognizant of very, very important elements of the ecosystem, which play a role, nature's services, but which are disregarded in our very instrumentalist kind of way of looking at nature. But also thank you for underlining how processes that seem wasteful, like for instance, over and over again, even in the context of this rather quixotic idea of the Garland Rivers project. There's a constant talk of how the water that pours into the oceans is wasteful, for instance, or deserts are seen as wastelands, or there's really no understanding of these deep processes in the ocean of regeneration that you pointed out. So I think that that message goes out very, very forcefully. But also, thank you at the end for this very provocative questioning of what seems to be on the whole a liberal, ecologically aware direction in policy. So I'm going to begin now not with the technical question, but a question of how you see yourself intervening in these public discussions, and what kinds of solidarities do you work with? I know this is a somewhat biographical question, but a subtext of what we've been doing here also has to do with how these adversarial critical ideas can achieve greater traction in society at large. So could I draw you out on that? Because towards the end, you also invite us to question things that a lot of people take on trust, civil society initiatives, think tanks, and so on. Yeah? So that would be my first question.
I think you make a very valid point, Ranjit. I think we have been rather complacent and not too curious, even as within the scientific the disciplines. I think we ossified ourselves by working in silos, and we tend to work in, say, tropical ecology or tropical forests, and we don't care about something else, right? And the connections between disciplines, and I think across disciplines, it's something that I think scientists need to now, they have to be taught this, because I think what happens in terms of pedagogy is that scientists tend to adhere to the systems which give them higher learning. Now, this is where the beauty of the humanities come in, because the role of counterfactual is something that is sneered upon in the sciences. So for example, a chemist does not really talk to an astrophysicist or say a biochemist or a hydrogeologist. Now, I don't see any difference between any of these disciplines. I think all of them need to be speaking to each other and learning from each other. There are new methods, there are new techniques, and there are also, you need to understand the behavior of different processes within nature. Nature is not a single entity. And this is where I think scientists have been failing. And I think they cause greater harm to their own science by not being more inquisitive or challenging the limits of understanding the remit in which nature operates. And I think by being fixated on a single technology or being fixed on a single hypothesis and trying to prove that during a lifetime, I think it's a hugely dangerous idea. And I think we need to question that. I think we now need to bring in critical thinking in the sciences. I mean, the question is a bit like, I find it a little, across institutions, whether in most countries, I mean, I find it little bit like Babugiri, that, people do not question their superiors, that how do you know this? How did you know this? When do you know that this was right? Or is there an anomaly to this phenomena? I mean, how can you be so certain about this? I think, and that should happen not just in biology or physics or chemistry, but across disciplines and within disciplines. And I don't see this happening enough, even in the best of universities. I'm a little skeptical about the way science is taught, and I'm also not sure whether scientists are reading enough of other sciences. I mean, if there is something like another science. So first of all, we've kind of created these other sciences and, kind of created limbs, which I think is atrocious. And I think this is where I thought people like Harold Urey, who I mentioned, or even several people, I mean, polymaths just don't exist anymore. We just have specialists who design products that have to hit the market, or they're people who are working towards a scientific problem, looking at a certain technology. And I think all of it is geared towards that. And I think that needs to be, seen through. I don't know if I'm making sense, but I thought that's my 2 cents.
No, absolutely. Thank you for spelling all this out with the courage that you've just done. But it set me thinking also about a time in, let's say, the 1950s or 60s, particularly because you've chosen to stay on and work in an Indian institutional landscape. There was a certain accent on, if you will, a kind of cosmopolitan understanding of the sciences. A very strange thing happened in the Nehruvian period. On the one hand, a driving commitment to big infrastructure projects, pulling the country out from its so-called backwardness to something else, but also, as for instance, in the figure of Homi Bhabha, a sense that you could link the arts, the sciences, the humanities, that this could be part of a larger education. What happened to that vision would be part of my question, but also how might the kinds of ideas that you're developing and articulating, how could they be part of a new curriculum? And how would that be disseminated?
I think that's a relevant question, but I don't think I'm aptly suited to answer that. But I think in the 50s and I think in the late 60s, perhaps, I think that phase, I think we lost very many thought leaders, by the time of, the first agricultural policy, for example, 1976. And I think you talk about it in your lecture on forests, for example, the creation of the Ministry of Environment and Forests. Let's take that. I think we had lost very many thinkers who were the big picture thinkers, and we started to drive everything into a silo. And one thing started to dominate over the other. That happened to the basic medical research. It happened with basic paleontological research. I mean, there was some fantastic work that was happening till, say, the early 80s, where you had some latitude to start looking at things like, which were slightly esoteric, but very important to tell us about the past, as well as understand the larger remit of the scientific methods that actually drive nature. But all of that is now kind of forgotten. I don't know whether you know this. It's a very famous video. There were students at MIT who were asked, and they were all PhD and senior graduate students, and they were given a sapling. They were shown a sapling and they were shown a piece of wood, and they were said, do you know how a sapling became this tree and then became a wood? And most of these were not students of literature or theology. They were science students. They were students of chemistry and biology, and they didn't know how carbon gets fixed. And they had PhDs. So this was a very important, I think we are doing the same thing. We've not understood the crux of why we are pursuing a certain field of research. And I think it's been a gradual lack of vision and leadership at the highest level. And I think we've only followed what the bureaucrats and the politicians have been, orchestrating in terms of where education should go. And I don't think, I think in terms of public health, I think the COVID response is a big question mark. I think we've got so many things wrong. I think the same thing is true with environment, just as I shared, just 3 examples, and I can go on and say that, we need to do this, we should not be doing this. So those kind of things are issues that need greater reflection. And I think we need big picture thinkers who can step back and say, how do we solve this intractable problem? Is there somebody else who we can bring in to understand this? Is there another science or another scientist who's working on these 2 aspects together? So those kind of things are what interests me.
I have several more questions, but I'm going to ask our audience here on site and also online if there are any questions. Yeah, can you wait for the mic to come to you?
Thank you, Pranay sir, and thank you, Ranjit sir, for your contribution. I just need to make a small comment about the intersection of science and arts, and that makes me extra curious as a literature and humanities students uh, attending a science talk. So we can take inspiration of Albert Einstein, who actually interlinked science with philosophy. So we can carry forward in a similar spirit, we can carry forward the language of science and make it in a way more accessible to people and public who come from diverse intellectual and social backgrounds, because obviously we want to learn facts, but the fact is that we have made it very elitist, that we have to be a PhD or we have to have a certain university background to be able to understand science. But actually, forests are open to everyone, oxygen is open to everyone, carbon dioxide is open to everyone, water is open to everyone. So all these basic elements of science are actually accessible. Then why not the information about it?
Thank you for your intervention. Do you have a question?
Thank you. That was a very illuminating talk. I had a question, if you could just sort of expand a little bit on the ruthless sort of consumption and plundering of carbon in the oceans, and what is the pitfall of not putting it back? What would be the sort of longer term consequence?
Yeah, Ranjit, could I answer that?
Yes, of course.
Okay, that's a good question. I think, the overexploitation, I showed you the picture of lanternfish, that's the most abundant vertebrate in the world. Thankfully, it's not overharvested. It's only the South Africans, consume it. And it's a fish that I think has a constant stock of 500 million tons. It's a massive number. Now, why do I say that? Is because if you're talking about deep sea mining, there are serious issues, because when you say deep sea mining, you're talking about the deepest trench where there is tectonic movement, or there is movement, or what is called seafloor spreading. Now, that's the place where the carbon and the silicates actually react and stay buried for a very long time. And that's the place where if we have a thick treacle of organisms or organic matter, that's where the future petroleum and natural gas, or whatever it is, whether you want to use it or want it to stay packed, that's up to us in the future. But the fact of the matter is that we are preventing those activities from happening. We are interfering with the geological and the biogeochemical processes. And that's extremely dangerous. For example, damming. For example, acidification of Ganga is actually causing less and less carbon sinking that is happening, that should happen naturally. Now, we've got tanneries, we've got dams, we've got large cities along the Ganga, which have been, for a very long time, the organisms and the creatures that lived in the Ganga kind of, neutralized that effect. But it can no longer, it doesn't have that buffer anymore. So we now see that the carbon burial rates in the Ganga are reducing, and they're reducing fast. So I think you're right. I think, there has to be limits to, how much we need to extract. And there are some zones which we should not touch. I mean, not just for biodiversity, but for geological processes for the future, because they are integral to how the future or how landscapes would look in the future. But if we are interfering now, it's going to be detrimental.
Related to this, with dams, is it possible to dismantle and reverse their effects, or is it sort of like, because they changed the course of the rivers? Like if you even see the Narmada Dam Valley, it was the worst ecological disaster.
I think rivers are, ancient, landscapes. So if they are dammed for a short time, so think about it. I mean, they've been in existence. So Narmada used to be a seaway. It's just closed its mouth and it's become narrower, right? And it's evolved, and there's so many amazing stories about Narmada. We should do a special talk on that, but I don't know. The point that I want to make here is that, if we were to get rid of dams which are, say, 30 or 50 or 100 years old, the river is going to correct the mistakes that we've made, because there are going to be creatures whose, for example, migrating fish that come upstream would, if they exist in the wild, would come back. And we've seen this in a couple of places. There is an example from Bangladesh where they've broken a dam because the Ilish fish was not migrating up, and it hadn't done for about 3 or 4 decades, and it finally did come there and spawn. So I think there's another example from Jordan, where the River Jordan, of course, that's another natural disaster. But there's a small dam that was broken to allow a certain kind of fish to grow there. So
that's encouraging. Thanks.
Thank you.
I was also thinking as you spoke and as these questions came up, I was also thinking of how marvelous it is that you've turned our attention away from land to the water. I'm very sympathetic to that, because in other work that I do also, I tend to emphasize why the oceans have had an incredible role to play in also the development of culture. It's usually disregarded. But following your presentation, I was just thinking that so many of the decisions to be made there would literally be outside of territorial waters. Do you see that as one of the problems towards formulating some kind of global policy on, for instance, how to address the renewal of the oceans? Or is that a challenge that can be fruitfully explored by international fora?
I think, Ranjit, what has happened is that, we've had several treaties, like, for example, the Treaty of the Moon, and we've had the Treaty of Antarctica, 1962. And we've been quite disrespectful. I mean, it's only a clutch of countries that, 12 or 20 countries in both these treaties that are party. And yet we don't, and it's not very chaotic. I mean, it's to get agreement between a handful of industrialized countries. And yet we don't get that, agreement between. So I think there has to be some arrangement globally, which we say that, we are not going to be touching this part of the world. I mean, it might belong to France, for example, Challenger's Deep or Marianas Trench, or, those kind of places, which there might be islands close by which entitle a certain country that, they capture the territorial waters. But I think for the larger interest of survival of on the planet, I think we'll have to take these hard decisions. And I don't know, because this is where politics and economics should cease, and biology and science and future of the planet should be taking primacy. And I don't see that happening at all.
Bjorn, did you have a question? Do we have any questions from our invisible audience? No. Okay. So, in conclusion, then, Pranay, I'm going to really thank you for, to me, because I've so often sought inspiration from scientists and people who write on science, it's just been amazing that you've sought out a popular audience outside of expert culture, both in Indica and in your present book. So thank you for opening up these discussions, which normally are just tightly held, and then we, at large, suffer the consequences. But this is, marvelous. Also, specifically from your talk today, I was so struck by a number of the very evocative conclusions you drew. I mean, I was struck by when you talk about the cyanobacteria, you say something amazing. You said, we are challenging the dominance of a humble creature. And it just struck me that there is, in so many ways, your presentation questions the kind of species sovereignty that we've brought to bear on this planet from the time of the Enlightenment, from the Industrial Revolution, which really has led us to not see the complex play and the interplay of organisms And if these last 2 years have taught us anything, it's precisely that something that you can't even see as just, it can besiege you, it can lay you low, and that itself should be a lesson. Also, the way in which you showed us, beyond the cliche of a documentary title, what does it mean for this to be a living planet, that its processes of formation are still current in the Earth's deep places. So it's been both technically enriching and also philosophically and from a speculative point of view, it's been it's really been a very provocative lecture. And I do hope that these ideas will ripple out from all those of us who've heard it today to the larger public sphere. Yeah, so thank you very much indeed. And Pranay, all the very best for your new book. And thank you for joining us, and thank you for speaking to us this evening.
Thank you for having me, Ranjit.